in that case, it's always direct toward the equilibrium position. And is proportional to the position of the particle. So this kind of this kind of motion, we classify it called simple harmonic motion. Simple harmonic motion. So basically, we're going to study this motion. And basically, this is it, the spring motion. That means if you push the object down like this, for example, this one. So this is the equilibrium position, right? Like this. Okay, now if I push down, you oscillate up and down, oscillating up and down. Then always direct toward the equilibrium position. So we move up to here and try to get back here. And because the kinetic energy push you further, and then we have to go back. This oscillation motion direct toward the equilibrium position is called what they call the simple harmonic motion. The same thing with this simple pendulum. And then if you position in here, you always try to go to the center. And then it swung past the center, and then go to here and return back again. So that's serving the position. Our job in this chapter 12 section is how can we express this type of motion in terms of mathematical terms. In this case, they like to express this function in terms of differential equation. So we already know in these cases, one picture worth million words. So for example, you plot x versus t. In these cases, you set like this, a straight line. Then you know, you see a line like this, it indicates what? Constant velocity. Constant velocity. Okay, velocity curve, because you can express x equal to v times t. So that's constant velocity. That means you look at the equation, then you can picture the diagram, and then you know physically what does it represent. Okay, you look at this, another type of curve. In this case, is something like this. Okay, if this is x versus t, you think, this is x versus t is equal to quadratic equation. Is related to a constant association. In which case, x is x equal to x of I plus v times t, v sub I times t plus 1.5 at squared. So you can look at it. So this is from a line, from an equation, you can predict what kind of motion associated. This is the things that we would like to do for you. So now we like to go to from another point of view. In these cases, if you take the derivative, that means dx dt equal to v is constant. Then you express the derivative function representing what we call constant velocity motion. Now, if you do this one, you take d2x dt2, that equal to a. That means the differential equation derivative to the second order equal to constant. It represents this motion, represent this curve. So now we move forward. So we like to describe another type of motion. In their cases, this particular type of motion called simple harmonic motion. How does it do it? Derivative is going to develop this sense about a particular motion, a simple harmonic motion, can be representing a standard differential equation. So, well, how does that look like? So now we try to go on. The things we like to start on is the spring motion first. We know the spring motion is related to, very important, is related with Hooke's law, in which case is section 12.1. In that case is motion of a particle attached to a spring, attached to a spring. From the Hooke's law, we like to say is from Hooke's law. Hooke's law is very important in their cases. That's what the Young's modulus is. From the Young's modulus experiment, you should know any material have the spring constant. Any material. This cloth does, your sock does, even your handkerchief does, and all those have the spring constant. From Hooke's law, F is equal to minus K. It's describing on the top. And what is F? F equal ma, right? F equal ma, according to Newton's second law. Newton's second law. So if it does like this, then ma is equal to minus kx. And ma is equal to minus k divided by mx. Ladies and gentlemen, this is the equation we want to study. A is associated with what? A is associated with the representative of association. Association is derivative to second order of the x, this x. So MA. So that goes into the section 12.2. 12.2, we are talking about representation for SHM, for simple harmonic motion. So that picture, that is a simple harmonic motion. So now we like to develop this way. A is equal to minus k divided by m. In the future, k divided by m has some significance. It's related with angular velocity. So A equal minus k times x. Okay, from this on, then A is equal to the derivative of d2x dt2. Okay, so now we're representing this d2x dt2 equal to minus k divided by mx. This is called, this is a differential equation, and we like to find out what is the solution. What is x can be satisfied this differential equation. For differential equation, we have a two-way to do. It's called trial and error. Okay, that's almost like physics. A differential equation is you know the answer already, and then you try out if that's the answer. So you like to find out the x is on the right hand side, derivative 2 times. So from the math point of view, saying that derivative or something, you return back to x. Derivative 2 times. What kind of function is like that? So I search your soul. Definitely, x cannot equal to ct, right? Because if x equals ct, a constant times t, then you cannot make it. You cannot return to original function. So the other function can be original function is sine and cosine. So now, so you said, suppose that this is x equal to something called a cosine t. Okay, suppose like this. Then you dx dt, then you go to minus a sine t. d2t dt2 x the second times equal to minus a times cosine t. Lo and behold, you return back to itself. So from derivative point of view, if you derive a sine function twice and return back to its original function. Now this is math, give us an instinct. So when we look at this, you say, okay, x must be, can be represented taken by the sine function or cosine function. So we like to take this